Hello and welcome to part 2 of the MBE tutorial. So as you remember, we left off last time at the alignments. I have a 15-minute limit. I did not realize I was already at the limit, so I apologize if the video cut off abruptly. I'll try to be more mindful this time of how we are doing for time. So, where we left off was me talking about using the spatial filter versus not using the spatial filter. So if you're using the spatial filter, you have a kernel, you set the size, you convolve each frame across the image stacks with the kernel of your chosen size. If you don't use the spatial filter, what your reference frame does is it takes all of the image stacks that you have and averages this frame across all of them. Which method you choose is of course up to you. Both methods are employed in the lab. So the average, using the average, for instance, the idea is that as you average the frames across image stacks, what that should do is cancel out the smaller, less relevant data for alignment and emphasize something like the blood vessels, which should be common throughout the image stacks that you have selected. However, if I was to pick, I would pick what we did not in fact do in the paper, and that is to actually use the spatial filter. The problem that I see with using the average is that it will, if we have some spontaneous brain activity that is actually common across all image stacks that we don't actually want to use for alignment because, say, it's only common for some of them but not common for all of them, then if we average across that, we're actually going to emphasize that over here, and then that might actually mess up our alignment. Of course, that probably won't be the case for most experiments, especially spontaneous activity from GChem6 data. So averaging it across it for our purposes is okay, and we'll just go with that because that's what was done in the paper. So that concludes the alignment. So next we go to the set coordinate system plugin. This is a very important plugin that you'll always want to go through for any project that you undertake. So what we do here is we'll filter this so that we're only looking at the files that have undergone alignment. And as you can see over here, every single processing step that a particular file goes through, that processing step is concatenated onto the file name. So what we're going to do here is set the coordinate system, which means selecting your origin. What I'm going to do is I click on the screen over here, and whenever I've done this, I've always had an expert with me to point out where bregma is. So what we're doing here is we're looking for the anatomical landmark bregma, which to my untrained eye I think is over here. So you can see over here on the right, the origin for this has been set and has actually been saved for that file. So if you exit this project and reopen it, the origin that you've selected will actually stick with the file that you've clicked. So I'm going to click this for multiple ones of them because I'm not very sure. Note, of course, that we are taking the data after alignment. So after alignment, these files should be okay for having a common origin. Of course, before alignment there might be a shift, so you shouldn't necessarily set the coordinate system before you've done alignment unless you're sure that your data is well aligned. So after we've picked all these files, what I do is I average across all of them. So what I've done now is we've taken the origin for each file that we've collected and averaged over them to create one origin over here, which is then set globally as the origin for all files. So for instance, we go to a random plugin over here, you can see again the origin has been set to be over here. So this is now set globally. Because of this, the set coordinate system, I will eventually have it that it'll actually be on the left here. So for instance, you can imagine X and Y for the user to manually set. And the reason it's on the left here because this is something that's not self-contained in a particular plugin. Excuse me. I'm actually defying my own design principles by putting this in this plugin over here. So in the future, you should see a X and a Y over here for where you can manually set it. However, it's nice to have this plugin where you can, for instance, average over selected origins and then average over that to set the origin globally. So the next thing you want to pick over here is your pixel width. So we know, for instance, that each pixel is 41 wide. So you can see here what I've just done is if you look at a single pixel, so a single pixel from there to there, there's now 41 units between the two. And as we've said, we've picked 41 microns. If we zoom out, and that looks nicer. We are now looking at our data with the correct pixel width and the correct origin. Note that at this very moment, selecting millimeters or microns, all it really does is change the X and Y axis. This is because mathematically, as we'll see later, as I'll explain a bit later, it cancels out when you import your particular coordinates. If you use the same units and the same units for whatever you're importing in, it doesn't really matter that you specify what the units are over here. The purpose of this selection tool over here isn't just to change the X and Y coordinates. In the future, you should be able to use this where you, for instance, pick microns here and you set your pixel width in microns, but say your data and your coordinates that you're importing. So in the application, you can import coordinates for particular brain regions. Say that's in centimeters or millimeters. Then it's nice to just quickly be able to import in millimeters, but have this in microns, and then the application will, in the background, work out how the conversion happens. Also note, we'll probably have a nanometer scale here as well for those, since 1 micron is the size of a bacterium. So if for those doing cellular data, you might want something even smaller. But yes, just so you know, this doesn't currently really do anything, but it will in the future. So next we go to the crop plugin. This is also a pretty important plugin. So we go post align to our data, and now of course what we want is to create a poly ROI that makes sure that we get rid of all of the bone. Make sure that all that we're getting is the nice brain data. So usually I'd actually be a bit more careful with how I'm doing this, but this will work for our purposes. Create another second one. To connect the end, so to connect end to end, you want to click the right mouse button after you're happy with how things are. Okie dokes. So you can see on the right here are our two ROIs. You might be wondering what in the world's with the name. That is, of course, this is just a unique identifier automatically made for the ROI, so that it doesn't override anything. So these two actually have already been saved to file. And I mean, if we exit the app and open it again, they should appear. So you can actually double click one of these and then say left. Let's just call it left and right, and that will rename your ROIs that you've created. So right, that's nice. So to crop the data, we want to select, so we can again imagine there's 31 files here. We select all the data we want to crop, we select the ROIs, and we crop to those regions of interest. Right, so the processing is complete. We can see, okay, so the filter doesn't actually update immediately. So if we go, for instance, to the next plugin, we'll see over there crop as an option. So yeah, I just went from one plugin back to this to update this. You can see that's a bug that I'll fix later. So filter this to crop, and here we can see all of our crop data. See that it's not perfectly aligned at all. This is okay for our purposes. So I would also like to note that you can move your regions of interest around after you've made them. This won't save it in that location. However, if you do want to save it, say we move it here, we right click it and then we save, and then that'll be its new location. You can can also copy the ROI or remove it. Next, we go to a temporal filter. So let's say that we've cropped our data. We now want to apply a bandpass filter to get rid of brain activity that is too fast, so say hemodynamic artifacts, or too slow, so vascular artifacts are the slow ones, and the fast ones is artifacts that might be due to heart rate. So that's not brain activity. We have a frame rate of 30 Hz as we've collected the data, so this also needs to be specified. So we apply the filter. Right, so the filter has been applied. If we go to, again, it doesn't update immediately, the Chebyshev filter in the top right, we should see temporal filter. And now this is data that has already been temporally filtered. This was a Chebyshev filter that was applied. Note that in the future there might be a drop-down list over here where you can, for instance, select whether you want the Chebyshev filter or a Butterworth filter. And yes, next we calculate delta F over F, so the change from baseline. In the top right, again, we select everything. And then at the bottom here, we actually don't want to select anything. So what this is at the bottom is you're selecting what your averaged, your F0 source is, so what is averaged over. This might, if you just select these three, then we say double click this to deselect it. What's going to happen now is delta F over F is going to be computed by taking the difference for each of these within the data itself. So averaging for F0, it'll be computed for each of the image stacks themselves. So actually I'll do that so long. So why do you sometimes want to have F1 sourced from somewhere else? This is useful if you, for instance, have applied global signal regression before this step, because global signal regression is then going to make the data deviate around 0, and if you average over that, that causes all sorts of problems. Right, that was fast enough. So, global signal regression, again, we now want to go to df over f. So this is the data, as you can see here. There's some nice delta f over f activity. You can ignore the flicker in the background. That is a bug we're aware of. It's just a visual bug. It just means that it's not scaling properly. And this still shows you what is going on. So it's not a function defeating bug. Over here, we're going to apply global signal regression. So global signal regression can be used to remove spontaneous fluctuations by applying the general linear model. However, I would like to warn everyone that it has been shown to introduce negative correlations. So see Murphy et al. For a paper showing that. And that's not my Murphy, my PI, that is another Murphy. And this may be unsurprising because some studies have also shown that the global signal can be highly correlated with neural activity. So if you want to remove that, your end data might look nicer, but you might be removing something that's actually pivotal to what you're trying to study. However, you might not. There are arguments both ways. So just so you know, using GSR, there is controversy to that. So we're reaching the time limits here. So next I'll actually just go ahead and do the concatenation so long, and then after that we'll start with the seed placer. So concatenation, really, you just pick all the files you want and you concatenate them, and that's gonna concatenate them all into a single file. So you can imagine for our case we had 31 files and they were all concatenated. This required a lot of memory, and it would not have been possible if we did not use a CPU with considerable amount of RAM. So we had 32 gigabytes of RAM to do that. So yeah, this has been done. I'll see you in the next one.